which do. So today we'll start first with some new ideas on MATLAB. So let us go first. What is there in MATLAB? Let us see. Hmm, see. In MATLAB, we have seen MATLAB environment, its features, and the vector and matrix operators. So today we'll see some more features which is used to create a MATLAB program. That means a .m file. So that is what we'll do first. Then we'll see how we can find out traction vectors by using those ideas. So in MATLAB, we'll create a program to find out traction vectors from a given state of stress matrix and for a given direction. Okay. That means for a given plane which is indicated by outer normal. So that outer normal line has three direction cosines which will be provided to the program and thereby it will output the direction cosines. That is what we will see, and the next part would be again in stress and deformation analysis. We'll again go back to the previous slide and discuss about the principal planes. Okay, how to find out the principal stresses. So let us start from the documents which are already downloaded in this computer, but for your reference, what you need to do is you have to see this particular these particular slides which are available from this website. So let us start first with this slide, which is some relational operators, and also let us discuss about some environment features which we didn't discuss earlier. These things we have discussed, but there is something more. Okay, this user defined functions, how to create user defined functions. Okay, that is what we'll show you today. Okay. So let us go into that. And to create a function, you must know something about the relational operators, other operators are there. This is what we'll discuss first. Now you see relational operators are basically this type of operators which are equal to, not equal to, strictly smaller, or less than equal to, strictly greater, greater than equal to, etc. etc. And there are some Boolean operators also. Those are AND operator and OR operator. Okay. These two operators are needed in conjugation with this relational operators. You probably know about the truth table of and OR operation. We are not going to discuss on that. We'll be using them directly. And now the flow control. For that, to add some control features in our program, these are some of the inbuilt functions which are already available. Those are if, simple if, then there is if else, there is if else if, and else. So if can be used in various forms, various ways. Other control flow statements are for statement. We have already seen for statement. We'll see it. Then there is another type of control flow statement, switch. It is somewhat different than if, but there is a similarity also. Now, for and while, for as a particular way of using it, and similarly while as another way of using it. So that way, if, then this while, these control flow functions are basically user dependent. For a particular application, one program developer might use if function, other developer might use while. Okay. We'll see the features that are available to them. So break, continue, end, pause, return. These are control flow functions available in MATLAB. So this is the if statement. So this is the simplest form. If there is a condition which tests whether this condition is true or false. If it is true, then this action will take place and it will end. This is simple if. If condition, there is some action and it will end. Then you see here, this if can be further elaborated with else if. So this is first condition, this condition. So if this is true, something will happen. Then there is another condition. If this condition is not true, then it will test whether this is true. Okay. So if this is true, something will happen. Okay. Or if this is not true, then this condition it will check, then this will happen. And if all these conditions are not true, then there is a default condition. Okay. Else, this comment is the default comment. Say, for example, if you can give a message that none of the conditions are true. So, what we learn from here, this else if and else, they are optional. This is the fundamental if statement. It should at least contain a condition and an end. So these are different features of using if. So now this is another idea. An if block can include multiple else if statement. The if statement requires the end keyword that is necessary. Also, it can be nested. Okay, nested if probably is also possible. You might try to make use of nested if. The next one is switch statement, similar to if, but there is a bit difference. Here you see instead of the condition, there is an expression. So in switch statement, first the expression is evaluated. Now this evaluation value might be different. it depends on some of the value of the variables which is being evaluated within the switch expression. So let us find out what is the under square root of a, b and c, their square, their sum, we will evaluate. So this evaluation might become equal to 1, it can be greater than 1, it can be less than 1. Okay. And say greater than 1 value might be 2 and less than 1 value might be say 0. So case 0 will do some action. This is action 1 corresponding to this particular case express this expression value. If this is equal to case expression 1, then this will happen. If this particular case expression 2, this value is equal to the evaluated value of switch expression, then this will happen. There is a default condition here also. So this is similar to if, but its execution is somewhat different. Okay. So this is important. Here you see an evaluated switch expression is a scalar, or it can be a string. Okay. Might be the name of a person or something like that. It's a string variable or a scalar. Scalar means 1, 2, 3, 4 some value. Usually integer values are used here. This comparison of real numbers sometimes might be erroneous. That is why it is better to avoid a real number output from switch expression. Such switch expressions are not advisable. Okay. Now, what is the switch block test? Each case until one of the cases is true. That means under a switch statement, there can be any number of actions. Say, for example, switch and this expression might be something which can be anything from 1 to 12. And let us say if case 1, then we'll assign month equal to January. And that way you understand for case 12, we'll assign month equal to December. And otherwise, we'll display that there is error in switch expression. That sort of thing we can do. So switch block tests each case until one of the cases is true. Then this otherwise condition is there, and then it exits. This is switch expression. Next. Now for loop we have already seen, we have used also to create a matrix. It can be nested for I equal to something. Within that we can use for j equal to something. There are some comments in between. It has to be ended by an end statement. Similarly, in while there is a condition. So for statement doesn't take any condition. So rather, what is this index array? This I is known as a floating variable. Usually it is an integer value. And here we give an array which is basically the value of I. So this I takes up value of in this array from the start value to the end. Now, similarly, there is an increment value also. We have already seen what is colon operator. So that way we can give here 1 colon 1 colon 10. Okay. 0 colon 2 colon 10. So this I value is also used usually within these statements here. So you recall that we have already used this for statement to create a matrix. Okay. Example, and in while there is a condition. This condition is similar to that we have used earlier in if statement. Now, while that condition is true, whatever is here, that will be executed. And then you should be careful that there is some statement here which will make this condition false. So this is a danger with using while statement. So you have to ensure that there is a condition within the while loop such that the condition gets false. Otherwise, you cannot come out from this while statement. Your MATLAB will go on evaluating whatever is within this while loop. Okay, you will become what I should. You cannot come out that way. Your program will go on running and running. You have to exit the program by some other way. So be careful when using this while loop. So one of the uses say while I is less than 50, if this is our condition, then we'll do something and afterwards we have to increment I. Usually I is I plus 1. This condition we should give. Then we are sure that sometimes after 50 execution, I will become 50. So this condition I less than 50, it will become false, then it will come out from the while. So you have to be careful there. Now using those control equations, we can use some of them in developing our program. And then we are discussing about another feature of MATLAB, which is to evaluate roots of a polynomial. You all know what is meant by a polynomial. In general, a polynomial of degree n is something like a plus bx, a plus bx plus cx square plus dx cube, like that. If it is of the order n, then you are going up to some coefficient a, subscript n, and x to the power n. That is the form of polynomial. See here, this is the second order polynomial. Is a plus bx plus cx square. That is the form. A is 1, b is minus 1, c is 1. Yeah, b is minus 1, c is 1. Now a, this is a is minus 1, then bx, so b is minus 1, then cx square, c is 1, and phi is x. So this we can find out by giving these coefficients of the polynomial. So this automatically indicates that our polynomial is, it goes that way. So that means this is our A, this is B, this is C, like that. So that way, this would be x square minus x minus 1. So if this is given, then roots of p will give these values. Okay. So this is how MATLAB evaluates roots of a polynomial. Okay, and it represents polynomials by the vector of its coefficient in descending order. So this is how you have to represent your polynomial, not like ax square and bx, rather it is cx square plus bx plus a in this fashion. Now that you understand. Okay. This is a particular use to find out solution of polynomial expression. There are something more. Like, we were talking about symbolic variable. So these are the use of symbolic variable where we can carry out some of these functions. Okay, integration, other things. This we can carry out. But anyway, this is not advisable. MATLAB is not meant for that. Actually, this is another product of MATLAB because as we have seen in the first lecture, MATLAB has so many toolboxes. So symbolic math toolbox is there, which you need to understand and to learn to use this symbolic analysis within MATLAB. So some example of those things can differentiate on other things. So that way, in our use of MATLAB, in the MATLAB environment which we have discussed, we can also compute this integration or this differentiation, but that would be carried out purely numerically. So there is a difference between that numerical computation and this analytical solution. Okay. So that way, this analytic solution can also take up some differential equation, usually ordinary differential equation. But in our case, we can also solve numerical or ordinary differential equation through some numerical algorithm. But that way, it will be a numerical solution. So all numerical solutions has some approximation. There is inbuilt error, and this is done symbolically. Okay. So this was our symbolic evaluation. Now, one thing we must say now, which is about functions and operators, we have already discussed, that is there. But how to develop a function, okay, that is not shown. So that will show by using MATLAB as such. Okay. So this is MATLAB. What we are going to do here is to develop a code of our own. We'll be using a code. Actually, that code is already there, and the purpose of that code is to evaluate the traction vector of a given state of stress matrix that we are talking about. So let us load that particular function. So that function is already here. So this is the function, it is already developed. We'll explain the function here. See, the name of the function is stress analysis. This is a short form. Understand its default extension is .m. So this .m means it is a MATLAB code, program written in MATLAB. Let us open it with MATLAB. So this is the thing. It is open. Now let us start with this. Usually, the function name is the name of the file or name of your program. So, what is done by this? We are defining a function. So, this is becoming a user defined function. So, once it is loaded, so actually we have another option of how we have loaded this function. We have simply gone into the directory and we initiated the function by double clicking on this particular function name. So other option is we can go here, there is an open option. Okay. If we click this open, it will ask for a directory and then you can select some function from here. Like we have used a test2, we developed a function earlier. So we are not using that thing, that is also possible. We have loaded it that way. So this is name of the function. This should have been the first expression of your code. Now there can be function definition within a function. That we'll see that this particular function contains another function. So there is another function which is defined within the main function. Okay, fine. So this is the function and the definition is there within this function. That's all. Now, what are the other features? A function might have some output value. If it has an output value, then we indicate that by the name of the variable which will get output, and that is indicated within a square bracket. Let us see the other function here. Here you see this function. The name of the function is input stress. So it will give an output. So this output value is given by the variable name capital S. So this capital S has to be defined within the function body. So this particular function has an end somewhere. Okay. So this is end of our input stress function. And this end is the end of our main function of stress analysis. So here, this S has to be defined within the body of this function. It has got a name. Now, it is also possible that, let us go back to the beginning from here. Let us go back here. You see, this is name of the function. It doesn't have any output. But there is a possibility of providing an output also to any function. And then you see there is an parenthesis open and closed. So here, what we can do within the parenthesis, if nothing is there, this indicates that this function do not require any argument. Now, to understand that if this is a sine function, then it requires an angle to give you an output. But this particular one doesn't require any uh, argument. So that way, to find out roots of a quadratic equation, you have to give three input, A, B, and C. Those are the coefficients of the quadratic polynomial. Okay. So this is optional and it includes the list of arguments required to execute this function. Okay, now what this function does? Stress analysis, it creates a stress or it gets a stress matrix from the user and then it asks for direction cosine. And afterwards, evaluate the traction effect from there. So this is our main function, stress analysis. First part would be to get a stress tensor. Here, the stress tensor is a matrix, 3 by 3 matrix. There is a default value given here. To understand what is the default value here. Okay, this is the default value. If we execute this thing, this is the default value. But if you are not using this particular value, you have the option of providing a new stress tensor as well. See here, this means it displays something. Okay, whatever is written within this parenthesis, you have to give it within a code. It will be executed. This is a function which is inbuilt in MATLAB. You can see it. Okay. Whatever you will write here, it will get displayed. So if we execute this thing, it will give the display of display. This is what we have written. So display. So this will happen. So first is it is displaying. Now it can be a variable also, right? So what we did here, this is answer. Right? So we can display that also. If we display answer, we'll get the same thing. Okay. Let us give answer. So it will display the stress matrix once again. And then it asks for this whether you want to input a new stress tensor. Here 1 and 0 usually they represent y, yes or no. Now in MATLAB, it is always advisable to take this 1 and 0 value because those are integer values and you can use this integer values in your subsequent condition. Okay. So this is simply a statement, a display. Nothing is done here. Okay, understand that. Okay, it will display this. Input a new stress tensor. Options are 1 and 0. Now here, this input is input from the terminal, from the command prompt. Okay. So that way, if I say here, okay, Q equal to input, okay, then it will ask for a input. Just a minute, let us see. Is it necessary to have this thing? I don't think. Now, so this is default. You have to provide some text along with this input statement. So this part is essential. Okay. So it is asking for some input. If I give set 21 here, so Q will be assigned with 21. So this is the use of input function, inbuilt function. So what it is asking here? Enter your choice. This choice is 1 and 0. So this 1 and 0 will be stored in our variable case 1. Now, we already know what is if statement. This is the condition for if statement. And now you see, we are checking for equality. To understand, a simple equal to sign is an assignment. Like A equal to 3. That is an assignment, but equal to equal to. This is a conditional statement. You should keep it in mind. So if case 1 is equal to 1, so here it is checking an integer value 1 with another integer value 1. Then what it will do? It will execute this particular thing. Now, as this function is defined here, this is the name of the function which we have defined here itself. This function is defined here. Now, it is possible that the function is not defined within the present function body. Okay. So, there is a logic to find out this function. So, MATLAB first try to locate this function within the function itself, within the function body. If it is not available there, then it will go first into the folder where the program is there, the current folder. And if it is not there within the current folder, then it will go. So you see, this is the current folder. Okay. Within class.cug MATLAB, this is the folder name. This is the folder name. Okay. This is the folder name. It will search for here. Otherwise, there are some default path. Okay. Some path name are there. It will search for the function in those directories which are included in MATLAB path function. Okay. So that you can also test. Let us see what are the paths. You see, these are the paths which are predefined. Okay. So these are the default paths. Okay, already available. You can add something to it by adding a path statement. So this path is a statement also. This path is a statement. You can use it. Let us do one thing. Let us clear the screen. CLC. Okay. So here also we can include this particular path by a path statement. If it is not included, then during execution, it will ask for whether it has to be added in its path. So that you have seen earlier, here also it will happen. We'll add it to the path. Is clear. So this is about the function. Then if this is true, it will go there, this input stress, and this input stress, this function, what it does, it takes 6 values. Okay, 3 principal stresses, SXX, SYY, and SZZ. And then this is XY, and as we know that this SXY is assigned here as 1, 2, matrix element 1, 2. And this 2, 1 is also equal to S1, 2. So it is also SXY. Similarly, S1, 3, this is SXZ, understand? We are taking that value and it is also assigned here as 3, 1. So only 6 are unique values we require and it assigns all the matrix elements of S matrix. So this is our output. This S is our output here. Okay. S is output. So S is created here. Right. When S is created, it displays the new stress matrix and it ends. The program ends there. Clear? Let us go back to our main program. So this is the thing, right? So here it ends, and if we are happy with this particular stress matrix, which is already defined, we will give an input 0. Here we will give input 0. This is not executed. This will not be executed. Otherwise, we will get a new stress matrix. This part is done. The next part is to get direction cosine of a plane. So that direction cosine is given by outer normal, and outer normal has three direction cosines with x, y, and z. They are, say, those are nx, ny, and z. It is represented here. How it is represented? It is represented by direction cosine. Okay. The value is dcm is taken as a vector 1 into 3. Single row, 3 columns. Those values are this nx, ny, and nz values. Now there is default values are given here. Right? If you are happy with this, this is fine. Otherwise, the same thing, the same logic. Give your option. This one will ask for new values. So there is no separate function here. It is done within the main function. And here you see these three values are taken within this for loop. Now understand we have used a for loop here and it will execute 3 times. 1 to 3 default increment value is 1. So the values will be 1, 2, and 3. It will execute 3 times and it will take the values. Enter direction cosines. And how they are assigned? They are assigned in this DCN variable, which is a subscripted variable, and it is taking first, second, and third values are our nx, ny, and nz. Right? So this is done. This n is end of this for statement. Right? And what is this end? This ends the if statement. Is that clear? Now what will happen? Now see, any direction cosine values we cannot give here. There is a restriction on direction cosine values. You know that what is the logic there? If direction cosines are L, M, and N, then L square plus N square plus N square has to be 1. So that is tested first. So if this is not done, there is some error in input that we need to check. So these are some features which you must always incorporate in your program. As much as checking, input checking should have been there. These are known as programming practices. You should include those things. Checking for errors. So what is the condition here? So first, that quantity, say if this is L, M, and N, L square, then this is M square, and this is N square. This is evaluated L square plus N square plus N square. Then it's square root. So this is assigned in another variable, which is square root of DCN squares. This is the new variable, And what we'll check now? Now, you see, we are not sure whether this output value is an integer value. Right? So that is why if we know that something is not an integer value, then we must not use this equality condition. This equality condition we should use for integer numbers. Otherwise, there is always a possibility of failure in the checking. Because in computation, there are some errors. Okay, those errors and other things, those are discussed here also. You see, first in numerical methods, that is our first chapter. We start with there. These approximations and errors associated with numerical methods, we all know that it is there. So this is evaluated. And here the checking, as it is not strictly for real integer number, what we are doing here, we have assigned a small value. This is known as sum accuracy value. And this thing, okay, this -1, ideally should be equal to 1. But from computation, it can be 1.001 or it can be 0.999, whatever it may be. So we are taking its difference with 1 and we are taking the absolute value. And if this value is greater than this, okay, so that means otherwise, if it is less than that, then our input values are okay. Otherwise, we will give an display that there is error in input. This is what will happen. And then we are calculating. So now we have some values of direction cosines. We have already obtained what is our stress matrix. S is already obtained. And what is our traction vectors? Traction vectors are simply matrix, stress matrix multiplied by the direction cosines. So anyway, it is not showing here. What happened? So there is equal to sign here. Okay. So now you see what it is doing. It is a matrix multiplication, or rather multiplication of a matrix with a vector. Dimension of S is 3 into 3. And what is dimension of this DCN? This DCN is 1 into 3. So they are not amenable for multiplication. So we have taken the transpose of that one. This is 3 into 1 and 3 into 3. So output value of T here is 3 by 1. So this is basically T vector. Okay. And actual T value, we should make it T vector. Right. And what is our T value actually? Let us put a semicolon here. It will not give any output. And our traction vector is this is T, right? This is T. So instead of DCN, what we must write here, this T vector. Okay. Is it okay? Is it done? So you should display also. What we should display here is traction vector. Then this is equal to what is the next display? This is T, right? Is it okay? This will display only. This display function, it will display only traction vector equal to what is there within the quote mark. But it is not displaying this T. Okay? To display this T variable, we have to make use of another display function. So what will happen in this case? First it will display this, and then the value of T will be displayed. This is fine. So let us run this. Here it has come. We'll add it to the path. Understand what is the meaning of this. Now let us see. Whatever. I should be able to change this partition. Anyway, you would be able to do it. So that way this window size you can vary. There is here, it is here, right? So what we can do, we have executed this program from this editor itself. So here, let us run this. Let us not give any input here. So this stress matrix we are accepting, we want to change it. Input is 0. Then it is asking for direction cosine. Again, we are not going to give any new value. Let us give the value 0. Okay, it has given a value of this traction vector. You understand? Now, anyway, whatever. The thing is, the name of this function is stress analysis, and we executed it from this editor itself by using this run command. But it is always possible to run it from your command line as well, because now this has become an user defined function. Okay. So that way here also, if we type this stress analysis, we do not require any argument, so no argument is necessary. We run it, the same thing will happen. Okay, this anyway you can give a choice of one, the other function will get executed. We are not going to show it here. You can test it yourself. So by the way, this will develop this function gradually. Okay, other things are there which we need to evaluate corresponding to the given stress matrix. So then this particular function will be given to you in a separate slide here. Okay, right now that MATLAB function is not here within the MATLAB. Some MATLAB features, comments, and other things are there, but no example functions are given. So we'll provide it here, stress analysis function. Okay, the function will be developed further. Now, what else? So far, we discussed up to this thing, evaluation of attraction vector. So this much we can do, and this is how we have implemented that in our MATLAB environment. So let us progress further with our theory part. That means here we'll elaborate further on this. We'll see what we can do with this Cauchy's equation and the stress at a point that is known. We have Cauchy's equation. From there, we'll find out the principal stresses and we'll plot those principal stresses in motion. So again, let us go into the files, slides which are downloaded here, but you can get those by clicking on this link. Okay, clear. So let us open that. Is there anything else? No. So this one is the slide. Okay. So we have discussed it. Okay, up to this point we have discussed, right? And what was there? These are the stress components at point 0 or point O, whatever you say. The stress components are this sigma 11 to sigma 33. These are the Cauchy equations. This is what we have seen. And in addition, this also can be computed by using MATLAB function. So far we have evaluated only this component T1, T2 and T3 of our traction vector. But we can also compute, this is the normal stress and this is the shear stress on this plane PQR. This tau is tau max, okay, on this plane. So this part we can do. And you understand that this sigma is normal stress here. If we take a different value of this direction cosine n, then this sigma value will change as well as tau value will also change. If this value is maximum, tau will become 0. And then we say this sigma value is a principal stress value. And corresponding direction for that plane, that means the values of n for that particular plane where sigma is maximum is known as principal stress directions. Right. So that is what we'll see now. Okay. So these three are Cauchy's equations, and these three sets of Cauchy's equations. This is the shorter form of this. So this part is the equation, or this is the traction vectors for a given direction n1, n2, n3. Now this is our matrix, sigma matrix. This indicates sigma. Now say for a particular case where this is a principal stress, okay, this is a particular value which is a principal stress. So corresponding to that sigma value, which is one of the principal stress value, we have a particular N1, N2 and N3. So this, if we use this particular direction cosines value corresponding to a principal stress value, this particular equation will get converted into this. Okay. So what we'll do from here, if this is the condition, then what we'll do, this we can write like this, is it not? You see this equation and see this one here. If we take it in the left hand side, then this is basically a 3 by 3 matrix which is sigma 0 0 0 sigma 0 and 0 0 sigma, right now. And if we take it in left hand side, then our right hand side is 0, and this left hand side can be expressed like this. Got it? Okay. So from here, this particular equation is represented like this. The coefficient matrix of these equations is this one, and then we can expand the determinant of this. So if we go on multiply, what we'll get? This sigma, this sigma, this sigma in the diagonal elements will get a sigma cube from here, right? Now, somewhere when we'll expand on this, okay, we'll get this one. It will give rise to some sigma square term. Okay, and again sometimes we'll get, say for this particular sub element, we'll get something with sigma, and there is something where we'll get some quantities like this. Here itself it is there, sigma x, sigma y, sigma z, which are some numerical values. Because in general, this is the given state of stress matrix. These values are known. What is unknown is this sigma, right? So what we have done, we have expressed this equation in this form. Clear? In this form, from here we have expanded this determinant, and then we'll get some terms with sigma. It's okay? Is there any coefficient there? You see? Is there any coefficient? This sigma into this sigma into this sigma. It is 1 simply. Right? So this is 1. But with sigma square, sigma and this constant term, there will be some coefficients. Okay. So that we can do. You can check it yourself. You expand it and you check it yourself that these coefficients values are this given by sigma x plus sigma y plus sigma z. Then with sigma we have these coefficients, with this I3 will get these coefficients. Is it okay? Now this I1, I2, I3, or rather in this equation, this I1, I2, I3, we could have written ABC or anything, but is there any significance of this I1, I2 and I3? Why they are named as I1, I2, I3? Because they are invariant. I stands for invariant, right? That means this particular equation is the characteristic equation of this particular matrix. So for a given matrix, as you know, the eigenvalues of this matrix are characteristic of this matrix. So these coefficients, they are also characteristics for this given state of stress matrix, and they need to be invariant. Their value cannot change. In this equation, this coefficient value should remain changed if we deal with this particular matrix. That you understand it? Okay, so they are invariant. So for a given state of stress, we can compute what are these invariants, right? And from these invariants, we write this cubic equation, and then we can solve this cubic equation. Okay. How many roots will be there? 3, because it's a cubic equation to the power 3. Otherwise, what we can do, we can find out the eigenvalues of this state of stress matrix. This eigenvalue of this sigma matrix will also give the principal stress values. But anyway, rather than going into the eigenvalue analysis, let us solve this cubic equation. Right? So how to solve them? Understand that here, whatever expression we are having here, what is the unknown? Sigma is the unknown. So this is an expression in sigma. I1, I2, I3, they are known for a given state of stress matrix. And if we use different sigma values, we will get different values of this expression. Right? So let us say the left hand side is a function in sigma. Okay. Let us see it here. So let us say the left hand side is a function in sigma, f sigma. And for different values of sigma, if we find out what is the value of this function and we make a plot, we'll get some plot. Okay. Now, you see how this f sigma is represented here. It is the same thing, our cubic equation, this was our cubic equation, you divide it by sigma square. This is sigma 1 minus I1 plus I2 by sigma minus I3 by sigma. What is the reason behind it? The reason is that whatever is the value of this I1, I2 and I3, they are finite values. They are not infinite values. Now, this sigma value, when we are making this plot, what is the range of this sigma? This plot we can make from minus infinity to plus infinity. Right? So whatever is the value of I1, I2 and I3, we can always assume some sigma which is much greater or much less than the highest and the lowest value. Now, you see, if our value of sigma is very less, okay, a negative quantity towards infinity, a very high negative quantity, what will happen? This is negative, this is negative, this is something, some value, some finite quantity. This is something less than this sigma. Okay. So ultimately it will remain a negative quantity. This is a negative quantity. So for a sufficiently high negative value, this f sigma value is negative. Similarly, if sigma is very high positive value, okay, there also this is positive. I1 is finite, it can be greater than this is positive. Here also this is becoming much less. So ultimately this f sigma has to be positive. So this is a positive value. Now we know that this f sigma is continuous. For every sigma value we have f sigma. And it crosses the zero line. F sigma value This is 0. This is the 0 value. On sigma axis, this is the 0 value of x. So in between, this dotted line shows that something is negative, it is changing to positive. There has to be a crossing between the 0 line. So that is one of the root. So if this is a particular root of this equation, this root has to be a real number. Okay. Now, if that is now a known value, this much we know. If this is a known value, then what we can do here, this particular quantity, or what it is shown here is that for this particular value of sigma, we know this sigma value is a principal stress value, and for that we can evaluate that n1, n2 and n3, right? It is also possible. This n1, n2 and n3 value for that particular sigma we can find out. Okay. Now, this state of stress matrix, it was developed for a given coordinate system in x, y, z. Then we have evaluated a particular principal stress value and the corresponding direction cosines for that particular principal stress value. And what we are doing now, our initial xyz coordinate axis, it is now oriented along the principal directions of this principal stress value. You see, this is the reorientation of our coordinate axis. Clear? Now say this z prime direction is the direction of this. Right? So if we orient it in this direction, what we know along this z plane, there is no shear stress. This already know, because in principal stress plane there is no shear stress. In such a case, what would be the nature of our stress matrix? In z plane there is no shear stress. Tau xz and tau zx they are 0. Tau yz and zy they are 0. So this is the new form. Okay. Now if we expand it, what happens? You see, this comes out as a multiplier, and the remaining one, here what we have is a quadratic equation. Clear? Now this is, if this is 0, in general this is not 0. Sigma 3 value is something. So this is equal to 0. And as it is a quadratic equation, it has two roots. This particular equation you expand it. You know the roots of a quadratic equation is given by this b by 2 plus minus root over b square minus 4s. Right? You put it in that form, you will find that the two roots of sigma, sigma 1 and 2, will come out like that. Hmm? You have to do it, it's not very complicated mathematics. You have to only expand this determinant, 2 by 2 determinant. Okay. Now, what are these quantities? This is a square quantity, this is also a square quantity. So, it cannot be something negative, it's a positive quantity. Its square root is something real. So ultimately, the roots which we will get from here, those two roots are also real. We have already seen that this particular root is also a real number. So ultimately, it proves that the three roots of this characteristic equation. So it's a proof that way. So that way, what we can see when we solve this particular equation, we'll get three real numbers. Solution of this equation. What are the solution of these equations? They will give us the eigenvalue. Eigenvalue means the principal stress values. Now in MATLAB, there is subroutine or inbuilt function for eigenvalue analysis, which gives eigenvalues and the associated eigenvectors. Actually, these eigenvectors are the direction cosines corresponding to the eigenvalues. But that way, we must not use this thing as a black box. Although it is known how to calculate the eigenvalue of a given matrix, it is done in numerical analysis. This is taught actually. In mathematics also, but basically numerical analysis is the implementation of some mathematical algorithm. So instead of that, we can use some numerical method to find out this equation. This is basically the solution of nonlinear equation. You did several methods there, like bisection method, then there is Newton's method, Newton-Raphson, regular falsi, etc., etc. Yeah, second method. We can use those things to solve this particular equation. So that is the thing we'll do next. There anything? And when they are known, okay, we'll evaluate we'll plot them in more circle as well. Okay, these are some of the problems we can solve it through MATLAB. And with that principal stress values, when they are known to us, we'll see how to develop more circle for a three-dimensional state of stress. Actually, this is the more circle for a two-dimensional state of stress. So the idea remains same. We'll be having a principal stress axis and we'll have a shear stress axis. Okay. And maximum shear stresses will also appear at the upper and lower quadrant of the circles, but instead of a single circle, there will be three circles, because here we have only xy plane, but for this type of stress matrix we have xy, yz and zx plane. So there will be three circles. The characteristics of those circles, other things we will be discussing in the next class. Is it okay? So let us stop here, and also we will be developing our program parallel so that we can solve these problems in MATLAB as well. Okay, so let's stop here today. তোমার বোধহয় একটা ক্লাস চলছে প্যারালালি নাকি?